Imagine this, you're sitting in a car about to accelerate. What makes the car move forward? What stops it when you hit the brakes? Why does a ball fall when you throw it up? And what's pulling you down to the earth right now? These questions are all about forces. And today we are about to unlock some of the most powerful secrets of the universe. Forces are everywhere, in every move you make, in every object you touch. But what exactly is going on behind the scenes? Stay tuned because we are about to dive deep into the forces that shape our world. And trust me, you won't want to miss this. But students, before we start, do not forget to like, share and subscribe to our channel. Let's learn together. Hello students, welcome in today's class. In today's class, we are going to begin with the new unit of physics which is about forces and momentum. So if you remember in the last unit, that is kinematics, we were discussing about how to quantify motion. But at that time, I told you that we will discuss motion, but we won't talk about its cause. Now, this particular unit, we are talking about that cause. So, we have to understand here we are talking about how force affects the motion of an object. This is what this particular unit is about. Alright, so without wasting any time, let's go through the curriculum. So, momentum and Newton's laws of motion. Understand that mass is the property of an object that resists change in motion. Okay. Recall F is equals to ma and solve problems using it. Understanding that acceleration and resultant force are always in the same direction. So again, in the previous classes you must have talked about all these things, but still we'll start from the scratch and take it to another level this time. Define and use linear momentum as the product of mass and velocity. Define and use force as the rate of change of momentum. This is very important. Here we are going to discuss how force is defined as the rate of change of momentum. How to apply Newton's laws. Describe and use the concept of weight as the effect of gravitational field. So I hope you have an idea of weight, but still we are going to discuss it from scratch. Next, non-uniform motion. Show a qualitative understanding of frictional forces and viscous drag. So this frictional force, the solid friction, this is something which might be entirely new for you, and we are going to discuss it now and do a lot of numerical problems involving friction. Okay. Then describe and explain qualitatively the motion of objects in a uniform gravitational field with air resistance. So air resistance or drag force, they are both the same. Understand that objects moving against a resistive force may reach a terminal velocity. Alright. So this is all what we are going to talk about. Then state the principle of conservation of momentum. Apply the principle of conservation of momentum specifically in case of collisions. Okay. Collision, that is of two types, elastic and inelastic collision. Recall that for an elastic collision, the energy remains conserved. So collision forms a very integral or crucial part of this unit. Understand that while momentum of a system is always conserved, some change in kinetic energy may take place. Don't worry, we will discuss about all these one by one. But now, what sequence we are going to follow? So first we will talk about the various types of forces that you should know or you are expected to know. Then various facts about forces, what changes can force make. Then Newton's laws, of course, the correlation between, of course, force, mass and acceleration. Then adding forces, and then we will also talk about momentum and impulse, where we will also cover the concept of collision. Okay, so one by one we'll start with that, but before we do that, like you can just write these down and then we shall start with the unit. Alright, so the first thing, what changes can force make? Okay, so you do understand what is a force or how do we define force? So, you know, the best way of doing it is that force is an agency which can cause a change in state of motion of an object. Okay, I will repeat. Force is an agency that causes a change in state of motion of an object. You might be defining force as simply a push or a pull, but now we will give a more sophisticated or technical definition to force, that we need a force if we have to change the state of motion. Imagine a meteor moving in space. So, do we need a force to keep that meteor moving? The answer is no. We don't need a force to keep the object in motion. If something is at rest in front of you, let's say the table in front of you, do we need a force to keep it at rest? The answer is no. So, whenever we want to change the state of motion from rest to motion or motion to rest or from one velocity to another velocity, we need a force, right? So, what can force do? It can of course change the shape, right? Then it can change the speed, it can speed up the object, it can slow down the object. If we have to do that, we need force, right? If we have to speed up the object, we need force. If we have to slow it down, we need force. Even if we have to maintain a constant speed but change the direction, even then velocity changes. Do you remember? Velocity is both magnitude and direction. So, even if the direction is changing, the speed is same, even then we will say velocity is changing and we would need a force for that, right? So, now do you have an idea that force means, something that can change the state of motion, right? So, you can write that down and then we move forward. Alright, so types of forces that I gave you an idea of, like we have to talk about weight, normal contact force, tension force, frictional force, spring force, drag force, upthrust, and these three, electric force, magnetic force, nuclear force, right, or let's say gravitational force, these are all called non-contact forces. What are these called? Non-contact forces. You don't need a contact between the two objects for these forces to operate. For example, if I release this pen, the earth will pull it down. So, earth is applying the gravitational force, but it does not need this pen to be in contact with the earth. While if you want to push the table in front of you, the force that you're going to apply is going to be a contact force, okay, the normal contact force. So, all such forces, tension, friction, spring, all these need contact. So, keep in mind we can classify all the forces as either contact forces or non-contact forces, okay. Alright, next thing, Newton's first law, we also call it as the law of inertia, okay. So, now what is that? So, just now I was talking about it, that an object will have a tendency to maintain its state of motion. So, if you have the table in front of you, it will try to be at rest. If something is moving, it will try to continue its motion. If that has to change, we need force, right? So, that's law of inertia. That is what Newton suggested in his first law, that for every object tends to remain in its uniform state of motion at rest or constant velocity unless an unbalanced external force is applied, okay. And then therefore, force is an interaction which causes a change in state of motion. So, can we say that it is Newton's first law that defines force, right? This is what Newton said in his first law, that force is something that changes state of motion. And also we should understand that mass is a measure of inertia, right? So, for example, let's say you have a pen in your hand and the table and you apply force on both of them. Would you expect the motion of both to change by the same amount? The answer is no. Maybe the pen will move quite easily, but the table will have more inertia. So, what do you mean by inertia? Inertia is basically the tendency to resist that change in motion. So, more mass can always be associated with more inertia, alright. So, first law is about how to define force and what governs the inertia of an object. So, inertia is obviously proportional to the mass, we can say in that sense, that inertia is correlated with mass. More mass means more inertia, means more tendency to resist the change in motion, okay. The object is said to be in equilibrium when resultant force acting on the object is 0. Now, what does this mean? So, imagine there is a block, okay, and we are applying two equal forces of 10 Newton. Let's say two people are pushing the block, one to the right and the other to the left. In this case, we would say that the block is under the impact of balanced forces, right? So 10 Newton and 10 Newton, the net force becomes 0, and in such a case, we will call that object to be in equilibrium. Okay, so one more term that we wish to associate with Newton's first law is equilibrium, that whenever net force is 0, the state of motion will not change. But imagine if this instead of 10 would have been 15 Newton, then we will say that there is an unbalanced force and that will change the state of motion, right? And then equilibrium is also of two types, static and dynamic. Keep that in mind. So for example, the table in front of you is in equilibrium, so that is static equilibrium. It is at rest for you, right? But a meteor moving in space or a meteorite moving in space at a constant velocity is also in equilibrium. It is not having any force acted on, on it. Even that is equilibrium. So keep in mind, equilibrium means when state of motion maintains, right? When state of motion maintains. So if like an object is at rest, we obviously call it as static equilibrium, and if an object continues moving with a constant velocity, then we call it as dynamic equilibrium, right? So that is something that you should understand about Newton's first law. How this is going to impact this chapter, we will shortly understand that. Okay, so next, before we go to the second law, so that is what we are doing first. We will discuss the three laws, but before we go to the second law, let's talk about momentum as a physical quantity. What do you mean by momentum? So for me, very simply to put it, it is the amount of motion, alright. It is the amount of motion. If I have to define momentum, I would just say it is the amount of motion. Now imagine what will decide the amount of motion. So you would say that, for example, if something has more velocity, that obviously has more amount of motion. For example, if you have to compare a bullet with a snail, let's say, so if you compare a bullet with a snail, so bullet is traveling at a very high speed, high velocity, it has more momentum. A snail would travel very slowly, then it has less momentum. So can we say momentum we denoted by P is proportional to what? Is proportional to the speed or the velocity, right? Next, it has to be proportional to the mass. Now let's compare that. Imagine there is a bicycle, someone's riding a bicycle at a speed of 20 kilometers per hour, and there is a bus full of passengers also traveling with 20 kilometers per hour. Would you like to say that both have the same momentum, both have the same amount of motion? Obviously not, because when you talk about the bus, there are a lot more people, there is a lot more mass, there is a lot more matter that has acquired that motion, while in case of bicycle it's much lesser. So can we say that more momentum we will associate with the system if there is more mass? Of course yes, and that is why we combine the two and we call momentum as, of course, mass times velocity. It is a vector quantity whose direction is same as that of velocity. Keep that in mind. So it indicates the amount of motion. Yes, of course, mathematically it is the product of mass and velocity, but the qualitative definition is the amount of motion. It is a vector quantity having same direction as velocity, and of course its SI unit is going to be kg times meter per second, right? Copy this down, copy down the important stuff. It's always advisable to make quick notes while you are watching these videos. This will give you more sense of retaining things. So I think it's a good thing that you should make short notes while you're watching these videos. So to do that, you can pause the video and copy down the stuff. Okay, so one by one we'll take it to next level. So right now I wish to talk about how to calculate resultant force when they are parallel to each other, right? So for example, if 200 and 300 Newton are being applied in the same direction, then we have the liberty to add them just like scalars, right? While if 200 and 300 Newton are being applied in the opposite direction, then the net force is going to be 100 Newton. So what does that tell you? That if both the forces are acting in the same direction, then you simply add them like scalars, while if they are acting in the opposite direction, then it's going to be the subtraction of the two. How we will deal with adding forces when they are not parallel? Don't worry, we will discuss that. Okay. So yeah, so I think we shall move forward. Now we come to the Newton's second law. Okay. So now, as we were saying, that when we apply force, the momentum of an object changes. Now, what decides the quantum of force? What decides its quantity? What decides its magnitude? Let's talk about that. So, what is the role here? What are we discussing? Force changes momentum, right? Can we call it like that? Force changes momentum. It changes the state of motion, right? More force is needed to cause more change in momentum in lesser time. Now, think of an example of catching a ball, right? Of catching a ball. I think you should all be able to relate with this. If you catch a ball and you keep your hand very stiff and the ball lands in your hand and it immediately stops, right? Then you feel more force. Imagine when you're catching the ball, you give it more time, you bring your hand backwards, what happens then? Again the ball is stopping, but you give it more time, right? You give it more time. So when you give it more time, you feel lesser of force, right? So can we say, and that is what Newton said, that there is more force needed if there is a rapid change in momentum. Okay, so before we talk about that in that sense, like this particular definition in that sense, in context of motion, what the second law you might have learnt in the previous classes is just that force is equals to mass times acceleration, that you need more force if you have more mass, or a greater force will give more acceleration, isn't it? So can we say F is equals to ma? Of course yes. But now what I want all of you to understand is a little different from what you have already known. So yes, of course, force is equal to the product of mass of the body and acceleration, we don't doubt that, but let's have another go at it. See how. Force is equal to the rate of change of momentum, isn't it? Force is equal to the rate of change of momentum. So imagine, what is momentum? Just now we were talking about it. It is mass times velocity, isn't it? It is mass times velocity. Now let's take a very simplistic case first, where the mass of the object is not changing, isn't it? So you are applying force on the table, you are applying force on the ball, the mass isn't changing. So can we say that since mass is not changing, so this can be written as m delta v by delta t. Now what is delta v by delta t? What is the rate of change of velocity? So you would say that's acceleration. Now you understand how I wanted you to correlate things. That force, in a way, of course it is mass times acceleration that you have been knowing, but it is also the rate of change of momentum. So can we call, or can we state Newton's second law as this, that force is equal to the rate of change of momentum? Of course yes. Okay, so that is what I wanted you to know. Now you can very quickly do this question. Take a screenshot, try this question, pause the video, and then we start with this to understand how we are going to apply this mathematically. Alright, so what is this question all about? So there is a 20 kilogram block and it is subjected to an unbalanced force, as you can clearly see. This is 50 and this is 10. So just to give you an idea, the net force is going to be what? 40 Newton, 50 minus 10, and that should be equals to mass times acceleration, giving us an acceleration of 2 meter per second square. So calculate the resultant force. You understand that now, 40 Newton. What effect does this resultant force have on the object? Because it was at rest, applying this force will obviously, cause this object to be in motion. What is the velocity of the object after 2 seconds? So let's do it. Since we know that the acceleration is 2 meter per second square, we can of course use A is equals to delta V by delta T, and acceleration is like 2 and change in velocity is what we have to find out, and time is also 2. So the change in velocity becomes 4 meter per second. So it will acquire a velocity of 4 meter per second. So now you understand force is needed to change momentum, and force is equal to the rate of change of momentum. That is change in momentum per unit change in time. Keep that in mind, and that is why we can say the unit of force is going to be kg times meter per second square, which is also of course called Newton, as you might be knowing. Okay, so that's the introduction of what Newton's first law is and Newton's second law is, and now we shall move forward. If you want, you can copy this down, then we move forward. All right, another question. Grab a screenshot and then we move forward. All right, so now you must have attempted the question, and now we are starting off with the solution. Okay, so there is an aircraft of mass this much takes off from rest in a distance of 1.25 kilometers. So that's the runway for you. The maximum thrust of the engines is 830 kilonewton. Calculate the takeoff speed. Discuss the assumptions that you have taken. All right, so the first thing that you should do here is apply the formula F is equals to ma, isn't it? Or from this we can calculate the acceleration is F by m, right? So what is the force acting? That's like 830 kilonewton. So let's multiply it by 10 raised to the power 3 to convert that to Newton, and then divided by the mass, that is like 3.3 into 10 raised to the power 5. So this is going to be 8.3 divided by 3.3. Let's do this calculation very quickly. So this is giving me 2.51 meter per second square. That's the acceleration, right? Now with this acceleration, it continues with for a distance of 1.25 kilometers, and we have to find the speed with which it will take off. So I think you should be knowing this equation, v square is equals to u square plus 2as, where we are able to relate the final velocity with the displacement. So v is what we have to find out. Initial velocity is 0, acceleration is 2.51, and the displacement is going to be 1250. Why? Because I have converted kilometer to meter. So let's do this calculation. 2 times 2.51 times 1250, and that's giving me v square is equals to 6275. And if we square root the answer, then let's see what we are getting. All right, so square root of 6275, so I am getting v as 79.2, or approximately 79.2 meter per second. That is the takeoff speed. So I think you should be able to do this question and your answer matches with mine, and if it does, then that's great, and if it is not, then hopefully you will learn with more and more problems that we do. Okay, next let's talk about impulse. So another physical quantity coming your way. We have talked about force, we have talked about momentum. Again, let me remind you, inertia is not a physical quantity in that sense. Mass is a measure of inertia. Inertia is a property, keep that in mind. Okay, impulse, it is the effect of force when a large force acts for a very short duration of time. So when we have a very large force acting for a short duration of time, that is where we majorly talk about impulse. For example, collisions. You catching that ball like that was an impact, that was an impulse, right? Collision of two cars is something related with impulse. An explosion may be an impulse. Okay, so mathematically it is the product of force and time. Now why do we do that? Because the force is of large magnitude, and the time of impact or the time of operating that force operating is very small. So let's again talk about how we stated Newton's second law, that is F is equals to delta P by delta T. So, can we write delta P is equals to force times delta T? Of course, yes. Now, normally in such cases when we talk about impulse, force is very large, okay, and time is very small, isn't it? So, a large, for example, you kicking a football, so the time for which the force acts on the football is very small, but that force is very large. So, this large quantity and this small quantity multiply to give us a decent number, right? So, this is what you call impulse. We denote, let's say, impulse by J. So, impulse is nothing but product of force and time, and we normally talk about impulse in cases where the force operates for a very short duration. It is equal to the change in momentum. So, now you should know that impulse is the change in momentum. So, what should be the unit of it? It should be the same as momentum, that is kg meter per second. A boy kicking a stationary ball of mass this much with an average force, the ball moved at 5 meter per second immediately. Calculate the impulse. Can we do that? Of course, yes. So, impulse is nothing but P final minus P initial. So, let us do this calculation. P initial was 0 and P final is going to be how much? It's going to be 0.4 times 5. So, that's going to be like 2. So, that's the answer for impulse, isn't it? That was easy. And then they are asking the time for which this, the foot was in contact with the ball, right? The boot was in contact with the ball. So, what can we do here? We can write impulse is product of force and time. So, impulse is like 2 and force is like 100 Newton. So, this will give us the time. So, the time is going to be, of course, 0.02 seconds. So, now you understand how impulse is different from normal forces operating. Imagine you pushing a table like this is not something that we will talk about as impulse. Impulse normally happens when the force operates for even fractions of second, right? So, it has a different context altogether. Keep that in mind. Okay, copy down the question if you want to, or grab a screenshot, then we move forward. All right. So, now let us talk about the principle of conservation of momentum. So, what are we doing right now? We are building up the basic vocabulary today in this class so that you are more able to eventually do the numerical problems that you are expected to know at this particular level of physics. Okay. So, now imagine we have a system comprising of multiple objects. Let's say, there is this basketball and this football, and these are two different objects. But what if we combine them as one system? What if we combine them as one system? So, even if the basketball would hit the football or the football will hit the basketball, whatever it is, but there is no external force on them. There is no external force on them. So, can we write F is equals to delta P by delta T? Of course, yes. But what if the net external force is 0? Then can we say that delta P is 0? That is, the change in momentum is 0. Means what? Means that let's say P initial is equals to P final. But when do we qualify for this? When does any situation qualify for this? So, the answer is going to be when there is no external force. So, imagine, let's say this basketball is hypothetically, let's imagine that this is of mass 0.5 kilogram and this is also of mass, let's say 0.5 kilogram. Okay. And let's say this is moving with a velocity of 3 meter per second and this is moving with a velocity of 6 meter per second and it collides with the football. So, what can happen is, let's say the velocity of the football becomes 6 meter per second while the basketball it becomes 3 meter per second after the impact. What do you see? Has the momentum of the basketball changed from 6 to 3? Yes. Of the football? Yes, it has changed from 3 to 6. The velocity has changed, the momentum has changed. But if you account for the overall momentum of the system, that has not changed. So, this is what we wish to talk about when we consider principle of conservation of momentum, that momentum can never change if there is no external force. That is what Newton taught us, isn't it? So if no external force acts on a system, then the total momentum of the system remains conserved. For example, when two moving objects collide, the total momentum of the two objects just before the collision is same as the momentum after the collision. So I hope you understand what this is saying and what is the condition attached or associated with it. You should know that to understand how things behave in general also. Okay, copy this down, then we take a numerical on this. Alright, so trolley A of mass 2 kilogram is moving at 10 meter per second, collides with a stationary trolley. All this you can read, you can try this question, grab a screenshot and try this question and then move forward. Calculate the final common speed of the combined system. So the velocity of the two combined trolley immediately after, okay, the impulse experienced by the trolley B and the change in momentum experienced by the trolley A. Okay, so let's do this first. Overall initial momentum is equals to final momentum. So what is this going to be? So the first trolley, the momentum is going to be 2 times 10, of course. For the second trolley, this is going to be 3 times 0. Why? Because it was at rest. And then this is a combined system of mass 5 kilograms because both the trolleys have combined as one. And now if we calculate the velocity, that's going to be 20 divided by 5. That's going to be 4 meter per second. So this whole system now is going to be moving with a speed of 4 meter per second, isn't it? Now the velocity, that is done. The impulse experienced by the trolley B. What impulse, trolley B would experience? So for B, let's calculate the impulse, which is nothing but its final momentum minus the initial momentum. What is its final momentum? So its mass is 3 kilograms. Its velocity after collision becomes 4. Initially it was like 0. So the impulse is going to be 12 kg meter per second. Okay. Then the change in momentum experienced by trolley A. Are they not asking the impulse only? Yes. So let's do that. How? Because for trolley A, they are asking the change in momentum only. So now listen to this carefully. So what is the final momentum of trolley A? So its mass is 2. It is moving with a velocity 4 after collision. Initially it was moving with a velocity 10. So this is going to be 8 minus 20. So that's going to be minus 12. Now what do you see here? That where trolley B has changed its momentum by 12, trolley A has changed it by minus 12. And that is why the overall momentum has not changed. So that is how you justify that, you might see a change in momentum of the individual objects, but the overall momentum has not changed. Okay. So what all have we covered so far? What are the various types of forces we are going to talk about? Then what is Newton's first law? What is inertia? What is momentum? What is impulse? And I hope you now are in the right mode to learn the topics further, even if you might have forgotten them from your previous classes, but this gives you a refresh of your memory, and you should be able to understand the chapter further now. Alright, so now let's talk about Newton's third law. Okay, so for every action there is an equal and opposite reaction. The pair of action and reaction act on two different bodies simultaneously. There's no doubt about it. Force can never be singular. Every force is accompanied with an equal and opposite reaction. That is what Newton suggested. You can take n number of examples. You push the table that we were talking about, you will always experience a backward force. You have to move forward. How do you move forward? Can you move forward by yourself without any help of something else? Of course, no. What you do? You push the ground and you move forward, right? So when you push the ground gives you an equal and opposite reaction, and that is how you're able to move. So what is the conclusion? That this particular law gives you the nature of force, that no force in nature can be singular, right? But then the question arises that if every force is balanced by an equal and opposite force, then there is no net force in nature. Then how can anything change its state of motion? So as I was telling you, that it's acting on two different bodies. So imagine if I have to move forward, I am pushing the ground is pushing me, so on me there is a net force, but if you combine me and the ground as one system, the net force is always 0, as we have just seen in the previous examples. Okay, and these two forces act simultaneously, of course, so there is no delay. So when you're pushing the ground, you are getting the reaction immediately, you don't have any delay over here. So it might sound very awkward, but the force that the earth is applying on the apple is the same as the force that the apple is applying on the earth. But then it doesn't have to be the same impact. Why? Because the apple is very light, it has a very less mass, so it will easily move towards the earth, but the earth won't move towards the apple because it has a huge mass. Force is the same. So what force is the earth applying on the apple is the same or equal and opposite to what the apple is applying on the earth. Okay, so that is what I wish to talk about in Newton's third law. Next thing, so this is something that force individually we have to discuss the various situations. Right now in this particular class today, we are just discussing what are the main types of forces that we are going to talk about, but how to operate them, how to use them in mathematical situations is something we will take up in the next class. Okay, so weight is of course the pull of gravity on an object. Contact force is a force that is applied by the objects when they are in contact with each other, as I was talking about. You can have this example over here where this person is being pulled down because of the gravity, but ultimately it reaches in contact with the ground. Now the question arises, is the gravity not acting now? Of course it is there, but it is experiencing a contact force from the ground which is making the net force on this person 0. Okay, so contact force is the force that obviously happens due to the contact of two objects with each other, but it is always perpendicular to the surface, and that is why we also call it as the normal contact force. So where is the ground applying this normal contact force on the person? Upwards. But where is the person applying the normal contact force on the ground? Downwards. That is Newton's third law for you. Okay, next, the gravitational field strength. So of course you do understand that we are all in the gravitational field of the earth, and it has a particular strength, it has a particular magnitude of force that it will apply on objects, and different planets will have a different value of gravitational field intensity. So for example, Jupiter has the maximum, but right now what we are mainly concerned about is the earth's gravity. Okay, the weight of an object depends on the strength of gravitational force acting on it. For example, objects weigh less on the moon than on the earth because for obvious reasons, earth has a stronger field. Gravitational field strength is defined as the force per unit mass. So of course, you should understand that every planet has some different field strength. So for every unit mass, earth has a gravitational field strength of 9.8 or approximately 10 Newton per kilogram, right? So for every kilogram, earth applies 9.8 or 10 Newton approximately. So then you can anticipate for, let's say, 2 kilogram, it will be applying 20 Newton and so on, right? On earth, the gravitational field strength is this, while the gravitational field strength on the moon is like 1/6 approximately, that is 1.6 Newton per kilogram. Okay, so this you should know to understand how weight operates. Okay, now let's do a couple of questions. An object is projected vertically upward. Which is correct about the net force acting on the object at the instant when the object reaches its maximum height? So imagine when it is at its maximum height, okay, shall we say its velocity is 0? Of course, yes, because when it is at its highest point, it reaches there and then it retraces its path, it returns back. So at the highest point, can we say velocity is 0? Yes, but should we say the acceleration is 0? No, the acceleration is still acting, right? So the net force is still there, okay? The gravity has not stopped acting. So the net force acting on it is 0. is a maximum, changes direction, is directed downwards. So the answer is directed downwards. All through this journey, when the ball was going up, when it is coming down, gravity was always acting in the downward direction. So the force is always acting in the downward direction. A stationary tennis ball of mass 58 gram is hit by a racket. The ball is in contact with the racket for a time of 10 meter per second and leaves the racket with a speed of, this is 10 millisecond and leaves the racket with a speed of 15 meter per second. Calculate the average force exerted by the racket on the ball. Alright, so let's do that. Force is equals to, of course, mass times acceleration, and to calculate the acceleration, that is delta V by delta T. So that's going to be velocity changes to 15 and the time is 10 millisecond. This is misprint of meter per second. This is millisecond what you have to interpret. Okay, so 10 millisecond, that is 10 into 10 is power minus 2. So this is going to be 1500 divided by 10. So that's going to be 150 meter per second square. Okay, so for that small duration, the acceleration is huge. That's 150. Okay, so mass is 58 grams. So let's divide it by 1000 to convert that to kilogram, and the velocity and the acceleration is 150. So that's giving me, let's do this calculation very quickly. 58 times 15 divided by 100, and that's giving me 8.7 Newton. All right. So that's an easy question. So what are we doing in this particular class? I hope you understand. We are revising all the Newton's laws and the basic terms, but then we will start this chapter as per the requirement or the types of question that we are going to get in the next video. Okay. Again, common types of forces: friction, the force that acts when two surfaces rub over each other, just to give you an idea. Okay. Air resistance is when you feel the friction due to the air or any fluid like water. Okay, then we call it as the drag force. Then there is upthrust, that is a force that you experience when you are in a liquid, and the upward force that you experience, that is called the upthrust, right? That happens because of the pressure, and we will talk about it in detail, but just to give you an idea, the upward push of a liquid or a gas on an object, the upthrust of water makes you float in the swimming pool. Of course, you have felt that. Okay. Then another couple of questions. A brick of mass 4 kg lies on a floor. A force of 20 Newton is applied downward to the brick. Calculate the magnitude of force exerted by the brick on the floor. Let's do this. So let's say there is this brick, okay, lying on the floor, and a force of 20 Newton is applied on the brick. Okay, so we are applying a force of 20 Newton, and since it is 4 kg, so the force of gravity is going to be mg. So g means the gravitational field strength, which we are taking for now, let's say 10 Newton per kg, okay, or 10 meter per second square. So what is the force that the ground is applying on this brick? Let's say F. We can also call it as the contact force. Now the brick is in equilibrium, and if it is in equilibrium, the downward force should be equal to the upward force. So the contact force should be equal to 20 plus 40, because this will become 40 if we take gravity as 10, and therefore this becomes 60. So are you understanding how we are using the condition of equilibrium to calculate the force that the ground is applying on the brick, right? That is what we have to find out. Calculate the magnitude of the force exerted by the brick on the floor. But we have calculated the force exerted by the ground on the brick, but is it not going to be the same? Of course, yes. That is Newton's third law. Whatever force the brick is going to apply on the ground is same as the force that ground is applying on the brick, just the direction is opposite. Next, a constant force of this much acts on an initially stationary railway carriage. Calculate for a time of 8 seconds the velocity. Again, this is something very easy for us. We have done such questions. So let's quickly do that. acceleration. This is just to give you a practice of things, and so that you are more confident before we start the the main thing of this chapter. So force is like 4 into 10 raised to the power 2, and like mass is 1.1 times 10 raised to the power 3. So that's going to be, let's do this calculation very quickly. So this is going to be like 4 times 100 and divided by 1100. So this is giving me 0.36 meter per second square. All right, and then we have the time, so we can use the equation of motion. V equals to u plus at. U is 0, a is 0.36, and time is like 8 seconds. So multiply this by 8. I am getting velocity as 2.9 meter per second. Easy. And the distance traveled, of course, we can use the equation of motion. S is equals to ut plus half at square. So of course, when you're learning this chapter, I'm assuming that you already know kinematics. So u is 0, and so let's just calculate half a t squared. So what is the value of time? So that's like 8 square. So I should just multiply 0.36 by let's say 32. That's giving me 11.63 meters, right? So that is easy. I hope you should be able to do that. And now we can take one last question, and we have built up the right momentum towards this chapter, and then we can start off with the next level of this chapter. An air gun fires 45 pellets of mass 2 gram each at an initial speed of 50 meter per second per minute. Okay, so 50 meter per second, 45 pellets, okay, every minute. What is the average force experienced by the gun? So that's another example of Newton's third law. So when you have the gun in your hand and the bullets are going forward, the gun is getting a recoil force in the backward direction, isn't it? So that's Newton's third law. That is what we have to calculate. So can we write F is equals to the rate of change of momentum? And now what is the rate of change of momentum? Oh, okay, so the rate of change of momentum is going to be delta P by delta T. So final momentum, let's calculate that. So there is the mass of the pellet is 2 by 1000 because we are converting that to kilogram, and velocity is like 50 meter per second. Okay, and the time is 1 minute. So let's convert that to seconds. But this is only for one pellet. How many pellets are being fired? 45 pellets every minute. So let's multiply that by 45. So did you try this question? Are you getting the same answer? F is equals to delta P by delta T. So let's do that. So this is going to be 100. So let's cancel the common factors first. Okay, now what are we left with? Let's say this is 9 times, this is 2 times. So this is going to be 9 divided by 120. So that's giving me 0.075 Newton. Okay, 0.075. Let's do the calculation again. So let's look at the calculation again. So the mass of the pellet was 2 grams. So that's why we divided by 1000, and the velocity was 50 meter per second. But this all information is given that 45 bullets were being fired every minute. That is why we multiplied it by 45 and we took the time as 60. Okay, so that's all for this introductory video of this chapter, where we are discussing about forces, momentum, impulse. The next class we will talk about every type of force in detail and see how they operate. And the most important part of the next class is going to be, finally, we will talk about free body diagrams. So that's the main thing of the next class. It's going to be very important. I hope to see you next time, but you first revise all this and then start watching that particular video. But that's all for this particular video. Happy learning. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.